what we're going to see is a bunch of search problems. So the input is going to be an array, always. Input is going to be an array A of some numbers and array A of, I'm going to make it as distinct numbers, just for the sake of simplicity. Distinct numbers and another number, let's say x, and output we want to know whether x belongs to A or no. So basically it's an yes or no question. Alright, so this is going to be the kind of questions you're going to see in this lecture. So let's start with the most basic version of this problem. What if I give you an array A of n numbers? I haven't specified the input size, but it is n typically. A of n numbers, and I want to check if x is there. If I don't say anything about the array, the only option I have is just go through the entire array, right? If A is unsorted, like we don't say anything about A, if A is unsorted, then all we can do is linear scan, right? There's no other option, and which is going to cost us of n time, where n is the size of A. On the other hand, if A is sorted, then we can do something clever, which we all know. Binary, which is binary search. And what exactly is binary search? Which is nothing but you have, let's take the array A, right? My first thing is I'll have a look at this position. Let's say this is position M, which is nothing but n over 2, the size of A divided by 2. Then what we will do is this. I'll just write the pseudo code. Yeah, let's try to be more formal, right? So search, binary search, okay. You want to search for a number x in A. So the first step is you find basically the middle element, right? So the middle element I'm going to call as, this is a middle element. Right? This is a middle element. Let's say M is equal to A of n over 2, where n is the size of A. Now if x is equal to M, then report yes, right? Report yes, and also what you can do is, if x is not equal to M and if n is equal to 1, that is the size of the array is 1, then report no, right? I'll just I'll make a ceiling for n over 2, because n over 2 can be n can be an odd number, right? Yeah, so if x is equal to m, then basically if x is the middle element, we are done. And x is the middle element, or the first element when the array size is 1, and if the number is not the same, then we report no. Otherwise, you kind of recurse on both sides, right? So if x is greater than m, then what I know is x has to be on the right side. So you recurse this algorithm. So search for x on the right side, which is n over 2 plus 1 n, and you search for x here. On the other hand, if x is less than m, then I know that if at all x is there, it has to be on the left side. So search a left side is 1, n over 2 minus 1, and x. So this is the pseudocode, and how to bound the time complexity. It is log n, but let's try to bound it using a recursion. So if I use t of n as a time complexity, what I can see is first I have to do some checks, and based on the checks I have to continue recursion on a smaller array of size n over 2. So that checks are going to cost you some constant amount of time, that let's say it is c. Then once I get the check done and once I take a decision, the rest of the algorithm will cost us t n over 2. And if you expand this, this will become t n over 4, t n over 4 plus 2c, then t n over 8 plus 3c. So in general, t n divided by 2 to the I plus I times c, right? And I know that when the size of the array is 1, right? We can do this in constant time. So we want to make this quantity 1. To make this quantity 1, that is 2 divided by n raised to I is equal to 1. I know that n is equal to 2 raised to I, or I is equal to log n. So put all these things back. So this will be t of 1 plus log n times c. So the whole thing is big O of log n. So that is binary search. Yeah, this was just to refresh the memory. Now let's make it more interesting. So suppose the input array A is 2D. How are we going to check if x belongs to A? Okay, so it's a 2D array. It's a 2D array with n rows and etc. So 2D array, basically n cross n size, n rows and n column. And I will also give you an additional information that if you take the numbers within each of these rows, they are sorted. They are sorted in the left to right order. That means increasing. And also the numbers are sorted in the column order as well. Right? So when you go down, the numbers are increasing. When you go to the right side, the numbers are again increasing. And just for the sake of simplicity, let's assume that all numbers are distinct. All numbers are distinct. So let's see an example. So you may have number 2 here, 3 here, 7 here, 12, then 5, 9, okay, I said 13, then, so this number, the number here, since this should be sorted column wise and this should be sorted row wise. If you look at 3 of its neighbors, right, 2, 3 and 5, this number must be more than 5. For example, let's say 8 is totally fine. And similarly, if you look at this number 7, 8, 3, this number should be more than 8. Let me just put it as 36. So here again it has to be more. Let me just put it as 99. And now if you see, look, if you hear 8, 9, so let's say 25. So this has to be 49, just like that, okay? So this is a, this is a 2D array with things sorted in row wise and column wise. And now I want to find if X is in A or not. What is a trivial solution or the simplest solution? The simplest solution is this. Since these things are sorted row wise as well as column wise, what I can do is do a binary search on each of these rows. Or I can even choose to do binary searches, multiple binary searches on each of these columns. Since they are 1D arrays of size n, I can accomplish this task in log n time per column, right, or log n time per row. That means overall n log n. Can we do something better than this? Okay, so can we do something better than this? This is the next question. Alright, so there are multiple ways to solve this. Let me show one solution first. Again, let's try to apply this divide and conquer strategy. What I'm going to do is this. Let's say this is the n by n matrix. I'll divide this matrix into 4 parts. Okay, I will divide this matrix into 4 parts. Then let me have a look at the numbers here. That means these corner numbers. Okay, I'll have a look at these corner numbers and I'll see, maybe I just need to pick only one number, maybe just this number. And what I'm going to do is this. Actually, I can just pick these 2 numbers. Okay, this number okay, basically the last number within the first quadrant and the first number in the last quadrant, right? So what I'm going to do is I will see how X is compared with these 2 numbers. Okay, let me just call this number as A and let me call this number as B. Alright, so one thing I know is A has to be lesser than B, that is for sure. Right, so I want to see where is going to be X in this scenario. Okay, so there are different possibilities, right? X could be, so this is A and I know that B is more than A. So the number X I am looking for could be here, that is something smaller than A, right? Or it could be somewhere between A and B, or it could be something more than B. These are the 3 possibilities. Now, in the first case, suppose this is a scenario, that is the number is smaller than A. If the number is smaller than A, the X which I am looking for, X could be here, X could be here, X could be here. if x is lesser than a, what I know is x cannot be in this region. Sorry, x cannot belong to this region if x is less than a. Why? If x is less than a, what will happen is this region has all numbers greater than or equal to b, and since b is less than a, x is also less than b, so there is no way x can be here. That means we can forget about this region in this scenario, right? So x cannot belong to, I'm just going to give some name for these quadrants. So this is one, this is second quadrant, let's say this is third quadrant, and this is fourth quadrant. So in this scenario, x doesn't belong to the fourth quadrant. Similarly, if x is more than b, that means x cannot be in the first quadrant, right? If x is more than b, it could be here, it could be here as well, it could be here, or it could be here as well, but there is no way it can be here because b is less than or equal to x. That means a is strictly less than x, and all the numbers here are also strictly less than x. That means in this scenario, x cannot belong to the first quadrant. And now let's have a look at this scenario. X is between a and b. In this case, what will happen is actually both of these are going to be true. X cannot belong to this quadrant as well as x cannot belong to this quadrant, right? So x cannot belong to 1 as well as 4. So what I have done here is, I have divided this, the whole thing into 4 equal parts, and after doing one check, I can easily forget about one of this quadrant. In this case, exactly one quadrant I can forget. In this case also I can forget about one quadrant. In this case actually I can forget about 2 quadrants, which is much nicer. But let's think about the worst case scenario that you are able to avoid only one quadrant. Alright, so that is the algorithm. So now we need to continue the search in the remaining 3 quadrants, right? At most 3 quadrants. So if you write the recursion, let's say Tn, not here that the input size is not n, it is n square, but let me use Tn to denote the time for searching in an n cross n array. Okay, n cross n array with all of these properties like sorted and blah blah. Then what I can say is T of n is T of n over 2, right? So original thing I have, the whole thing is n, then these are n cross n, so I need to continue the search in smaller subarrays of size, sorry, this is n over 2 cross n over 2, and within how many of those subarrays I need to continue my search? In 3 of those, plus a constant, plus a constant. So let's try to expand this. So this will become, and we know that T of a constant is a constant, this will become three times 3 T n over 4, right, plus C plus C. That is nothing but 3 square plus 3 n divided by 2 square, right, plus 3c plus c. So if you open it again, this will become T of n is equal to 3 square plus 3 into T, sorry, now it is n over 4, so let me just make it as n over 8, plus C plus 3C plus C, which is going to be 3 cube plus n divided by 2 cube plus 9c plus 3c plus c. So looks like we can continue to 3 to the k divided by t n divided by 2 to the k plus the c I can take outside, 1 plus 3 square plus up to 3 raised to k minus 1. And this whole thing I can write as big O of 3 raised to k, right? So basically it's a geometric series with terms increasing. So we can kind of bound the whole thing by roughly the last term. Okay? So I can write it as 3 to the k n by 2 to the k plus c times t to the k. All right. Now I want to make this quantity is equal to 1, right? So for that I need to make 2 to the k as n or k as log n. So that means 3 to the log n multiplied by t of 1 plus c times 3 raised to log n, which is going to be, so what is 3 raised to log n? Which is nothing but n raised to log 3, n raised to log 3, and log 3 if you evaluate, log 2 is 1, so log 3 is definitely something more than 1. So this is going to be n raised to 1 point something, right? So what is log 3? N raised to, yeah, I don't know, but at least it's something more than 1. So what did we do now? What happened? Previously we were able to come up with a very simple algorithm which was taking n log n. Now we managed to come up with a very bad algorithm which will take us n raised to 1 point, I think it is about 1 point, at least 1.1. So n raised to 1.1 is definitely worse than n log n. Okay, so that was a bad idea. So this is a bad way of solving. We tried many complicated stuffs, but ultimately it gave us nothing. Okay, let's try another approach to solve this then. So that was a divide and conquer strategy, but it didn't work very well. Okay, so this is another strategy I'm trying to explore. So I know that the numbers are increasing in this order and also in this order. So here is another solution I have. I'll start with this number. Okay, I'll start here. Start on the right top corner, and I will compare this number with x. Okay, and what I'm going to do is, essentially what I'm going to do is I'm going to try to find if x is there in the first row. Okay, this is my first step. So, and for that I'm going to just do a very simple linear search. I'll check if x is here. Let's take a small example. Let's say x is 100. I'm looking for x is 100, and let's say the first number is 110, the second number is 98, then 80, 40, etc. First I will compare this number with x, and I see that this is more than x. So if at all x is there in the first row, it has to be on this side. So I can forget about this number, right? I can forget about this number, and I can also forget about this entire column, because all the numbers here are going to be more than 100. So I can forget this entire column. Now I come here, 98, and I see that 98 is more than 100, sorry, less than 100. That means the rest of this row can also be ignored. There is no way this can be here, right? What I will do next is I will come down, and let's say the next number is 120, right? So when I come down, I see 120, and I know that 120 is more than 100. So that means I can ignore the remaining part here. Now I try to compare the previous number. Let me just put some numbers. Let's say 108, 93, etc. So I come here, I see 108. Yeah, okay, I'm getting closer. And I come here. Now I see that it is 93. So I can ignore the rest. And I can also forget about this part. Okay, so this is the algorithm. And ultimately you're gonna reach here. I mean, if you don't find the answer, you're gonna reach here. So what is happening in this algorithm? You are making moves in this direction, like right to left direction, and also you are making moves in the top to bottom fashion. So whenever you make a move in the towards the left, you are able to ignore one entire column. Similarly, when you are making a move downwards, you are ignoring the remaining part of the row, right? And at each step, what is happening? You will make a comparison, and as a result of that comparison, you will make a move either in the left direction or in the downward direction, which means we can kind of bound the running time of this algorithm by bounding the total number of moves. And if you observe here, our algorithm is moving only towards the left side or towards the downside. So how many times you can make moves to the left? N times. And how many times you can move towards the down? N times. So the total time complexity is big O of N. Okay, so what we have seen so far is we had a look at the straightforward simple solution, which was n log n, and we tried to improve it. We thought of applying divide and conquer strategy. We did some circus, but we end up in getting a very bad solution, right? N to the log 3, which is like n multiplied by n raised to log 1.5, right, which was something worse than, right? This is clearly something worse than n log n. Okay, then we tried something new and we figured out that I can actually solve this in n, so better than the naive solution. Okay, so it's all good. Now the last question is, can we improve this further? Can we somehow come up with these are all like sorted arrays and everything, right? So can we actually come up with something closer to binary search like log n or anything better than big O of n? That is the next thing we need to solve. Okay. Okay, so let's continue. We already saw that the problem can be solved in O of n time, and now we are interested to see if this can be done in small o of n time. That is any improvement over n, right? Log n, square root of n, n over log n, n raised to 0.99, etc. Anything better than small o of, anything better than O of n. And we're going to see that the answer is no, which means there is no way you can have this, which essentially means the lower bound for this problem is omega of n, which also means this is, which essentially means the previous algorithm is optimal, or big O of n time is optimal. Alright, so to prove that, what I want you to see is, this is a small example. I want you to observe something. Okay, here the numbers are in the sorted order from left to right as well as top to bottom. But have a look at the numbers in this diagonal, that is off diagonal. 13, 16, something more than 13. Then 15 came down, 36 went up, 44 again went up. So in summary, there is no ordering between these numbers on this diagonal. Okay, there is an ordering this way, there is an ordering this way, but there is nothing here. There is an ordering here. These numbers must be in the increasing order, right? This diagonal, but this diagonal is completely unsorted. So keep this observation in mind. Keep this observation in mind. So diagonal is unsorted, specifically this diagonal. Okay, so let's see how the proof works. Our strategy is proof by contradiction, proof by contradiction strategy or technique. So what we will do is we will assume that this statement is true. Basically the opposite of what we want to prove is true. We will assume that. Then we will use that to prove something which is totally, totally stupid or totally impossible, right? Or basically we will try to come up with a contradiction, which means something is wrong with what we have done or what we have assumed, which essentially traces back to our original assumption. So let's assume that O of n time, assume that an O of n time solution, or there is an algorithm that can solve it in O of n time exists. An O of n time solution exists. Okay, this is our assumption, and we have to prove that this assumption is wrong. Alright, so what I'm going to do is this. Let's take another problem where I give an array, let's say B, given an unsorted array B of n numbers, search a number x in B. since B is unsorted, you have to scan the entire array, or you have to at least look at all the numbers in B. So that means we can solve it in O of n time, and we must use O of n, right? So the lower bound for this problem is omega n. All right. What I'm going to show now is, if this statement is true, then I can solve this problem in small o of n time, which is a contradiction. Okay, so how am I going to do this? What I will do is this. Assume that O of n times solution. So by solution I mean an algorithm. Let me give a name for the algorithm, which is let's say A star algorithm. Okay, there is another A star algorithm, but that's different. We're just giving a name. And what I'm going to do is, I'm going to construct a matrix like this of size n cross n, and what I will do is, I will take this off diagonal and I will copy all the elements in B, and I can just write them one by one, right? Because B is not sorted, and this diagonal of an array like this doesn't need to be sorted. Then I will fill these numbers with these columns, or these cells with some numbers, some random numbers, but I should make sure that all the numbers are strictly less than x. So all the numbers are strictly less than x, and they are in the sorted order, row wise as well as column wise. Similarly, I will fill this portion with some numbers, but I should make sure that all the numbers are greater than x, and also they are in the sorted order, row wise as well as column wise. Okay, which essentially means my new array, my new 2D array. Okay, let me just call it as a B dash. Okay, this is my original B, this is my B dash, which has B as the diagonal element, and everything above is smaller than x, everything below is greater than x, strictly greater than x. And I will ask, and I will feed this B dash, this new matrix, to this algorithm A star, right? And the algorithm A star is supposed to give me an yes or no answer, right? If algorithm A star tells me an yes, which means what? Which means x, the number x is there in this 2D array. And one thing I know is number x cannot be on this part because everything here is less than x. And similarly, number x cannot be on the bottom part because everything on the bottom part is more than x. So the only way number x exists in B dash is on this diagonal, which in turn means if the algorithm says x, which means the number x belongs to B dash, which means x actually belongs to B. Similarly, if the algorithm says no, that no means x doesn't belong to B dash, what I can infer is, I know that x cannot be here, x cannot be here, therefore x cannot be here as well. That means I can infer that x is not in B as well. Alright, so in some sense, I have used this algorithm A star to solve this problem, the simple problem, right? But I cannot feed this B directly. I have to make the input, or I have to appropriately change the input B to B dash so that it is in an acceptable format for A star, right? Because A star doesn't take 1D arrays. A star has some standards. So A star wants it to be n cross n, sorted row wise, sorted column wise, etc. So we'll make sure that A star is happy with all the requirements, and we'll just feed it to A star. All right. So now if this statement is true, that means A star is solving this in small o of n time, which means in small o of n time we can solve this problem also, right? Or I can say it in another way. If A star has given us a solution in small o of n time, that means A star has not even looked at n numbers. That's the meaning, right? Which means A star was able to give us the answer without looking at n numbers. Which means if that statement is true, that means we can even search in an unsorted array and find the answer without looking at all the numbers. That's what it means. Which is completely weird, right? Which is completely wrong. Therefore, we have arrived at a contradiction. So in other words, if the 2D array problem can be solved in small o of n time, implies searching in unsorted 1D array, 1D unsorted can also be solved in small o of n time. This is nothing but a contradiction. So now that we have arrived at a contradiction, we should kind of backtrack and see what went wrong. And obviously there is nothing wrong in these steps. These are our steps. So our steps are correct. So that means something must be wrong in what we have used externally. And what we have used externally is algorithm A star, right? So therefore A star cannot be true. I mean, the existence of A star cannot be true, which means you cannot solve this in this time, or the lower bound is omega of n. Okay, so that's the solution.